Afternoon, everyone. Welcome back from lunch. I'm going to talk today about some work that we've been doing at Kinfolk to enable multi-cloud across, in this case, both AWS and Packet, but I think some of the lessons will be hopefully interesting and generic to multiple environments. So first of all, just by way of introduction, I'm Andy Randall, and you may know me from this event last year. I was then with Tigera, so I'm one of the original founders of Project Calico, so I kind of came into this Kubernetes space and container space via the networking side. But since a month ago, I've been working at Kinfolk on business development. And at Kinfolk, we're really deep stack Kubernetes experts. And what this means is we have folks who are very deep in the engineering side, from kind of the top level service mesh all the way down to Linux kernel. So some links there if you're interested in finding more about what we do at Kinfolk. But hopefully I'll kind of explain a little bit more through some of what I talk about here. And just going to the title, obviously multi-cloud is there in the title, which is kind of the elephant in the room here a little bit. A lot of people talking about multi-cloud. It's a big buzzword, probably one of the most common drivers that people are talking about for Kubernetes. But I also hear a lot of questions from people who don't necessarily believe that it's a real thing, that people are actually doing it. And maybe this cartoon kind of exemplifies most people's reactions when you talk about multi-cloud, right? Multi-cloud, we're not even good at the cloud we already use. Well, it's like everyone says, when in doubt, double your technical complexity. So, is multi-cloud a problem in search of a problem, or is there actually a real problem here that we're solving and we're helping make people's lives better? So I'm going to give you an example of a customer that has done this, and some of the drivers behind it, but also some of the complexity, because absolutely it involves complexity as well. So there's kind of both sides of this picture are right. So I'm going to talk to you about a project we've been doing with a company called PubNative. Like Kinfolk, they're based in Berlin, and they do advanced mobile monetization, which is fancy words for mobile advertising on applications on your phone. Founded about 5 years ago, growing really fast. So just in the last calendar year, they grew the amount of traffic on their network by 10 times. And they're in 120 countries across the world. So very successful, born in the cloud, and all in AWS. And this is kind of the background of PubNative and what they do. And specifically the piece within the advertising ecosystem that they implement is something called the Supplyside Platform. So they interface with app developers who have a space in an application that they can place an ad, and the app developer calls the API. They then go and farm that offer out to a bunch of bidders, hundreds of thousands of API requests per second, typically running through the platform, and they'll feed an ad back to the application based on a whole lot of artificial intelligence that they apply to which is going to be the best ad for that user at the right price. And really, if you think about this business, there's kind of three things that you have to do well. So the first is obviously the core business logic. Their app developers have to be the top of their game. They have to know how do you match the demand side with the supply side well. Performance is incredibly critical in this kind of environment, because people don't take a lot of time before they'll click away to the next screen. An ad has to be served up in milliseconds. So one of the things that was mentioned to me was, just even things like the choice of programming language make a huge difference. They said if you're using an interpreted language, it's just not going to work. So they do a lot of performance optimization. And then cost, and because there's pretty thin margins, and you can't have your infrastructure costs being more than a few cents on the dollar of revenue that's going through the platform. So these are the kind of three key areas, and I think PubNative felt they were doing pretty well on the first two, but they were really struggling, particularly with this growth that they were seeing with the cost of the infrastructure that they were building on. So just to kind of step back and think a bit about the model of what they're doing here. Because for a lot of people, when they think about having workloads in the cloud, they focus on the cost of just the compute hours. I have so many instances at so many cents per hour. But when you're talking about farming out a lot of requests to all of these demand-side platforms that they're interfacing with, those bidders in that diagram, then you have a lot of egress data going out of the network. And these are not necessarily real figures from PubNative, but they give an example, give you an idea of kind of the ratio of costs of how much you might get from an application doing 100 terabytes of egress data, with maybe 10 48 vCPU instances with 64 gig of RAM. So, pretty significant chunk. That dark blue piece is spent on just the egress data. And they've been doing their homework, and they realize that even with discounted prices from AWS, by moving into a hosted bare metal environment with, in this case, Packet, they were pretty much getting half of the pricing that they would be paying on AWS. And you can see actually both compute and egress are significantly lower. In this particular example, I think in the case we're talking about, actually the difference on the egress traffic was even more substantial than this. But it gives you an idea of kind of what the driver is. Now you might look at that and say, $11,000, my application, I've got a lot of things to worry about. How much money do I want to spend, and how much pain do I want to go through to build a whole new environment, a whole new platform in a different cloud, and learn how to operate it, and all the challenges involved in that. And certainly, if these specific numbers were your bills, maybe that wouldn't justify it for you. But at some point, when you start to multiply this, at some level of volume, you're talking about numbers where this makes a substantial difference. And we'll come back and kind of talk about the business case specific to PubNative at the end, and kind of how much they've been saving. But it got to a point where this was a sufficiently large delta that they couldn't ignore it, and they came to us for help in taking the application they had running in AWS and moving into this multi-cloud environment to save money. And the strategy here was, and kind of one of the reasons why we're talking about multi-cloud rather than necessarily just moving everything into Packet is there's a lot of things that AWS does give you. There are some services that they give you, like S3 or RDS or other things that you might be using with AWS, which you might want to keep using. And there might be some workloads for which it's completely cost-effective to keep them there. And also, just for a perspective of reliability, if you're running across multiple clouds, if you are implementing a failover mode or a load balancing across those clouds, it gives you a level of resilience for either scale or failover that is an advantage. If you're going to build this, you might as well use that. But the objective here was to identify those specific workloads which had very high egress costs or very high compute costs, and move those specifically into the Packet cloud environment. And the key enabler for this, and why we're here talking at a ContainerDays talk, and why is Kubernetes was by this point, when they started looking at this, a very real option for deploying the application. They'd already started to move the application into Kubernetes in AWS, so if we could build a Kubernetes environment in Packet, then it would simplify the operating layer for deploying the application across both of these clouds. Some other things that they did like about Packet, one was you get access to the bare metal, so there's all sorts of optimizations and hardware customizations you can do on bare metal that you can get via an API. From a performance perspective, obviously there are advantages in that. But also for some folks, a security perspective, they like the fact that the physical machine they're running on, they know there are no other tenants running on that piece of hardware. And then, they have global coverage, so particularly for, I mentioned at the beginning, PubNative, 120 countries around the world that they're operating in. They wanted local presence. Just having a data center in Europe or a data center in North America wasn't sufficient. So these were all important factors. Now, when we came to look at it, though, it's not all plain sailing. There are some challenges when you start to talk about a bare metal environment, whether that's in your own data center or in a hosted cloud environment. You've basically just got a bunch of PCs with some wires coming into them. So you have to deal with that. You have to deal with the fact you've got access to the bare metal, you've got access to the underlying network. You haven't just got a nice, easy interface to say, give me a VPC, give me another VPC. And a lot of things that you might expect from a cloud provider, like a hosted firewall or load balancing, firewall protection of each host, just storage offerings like EBS, things like that, you're not going to get in a bare metal environment. And Packet makes no apologies for this. They are what they are, and what they do really well. They're not going to give you these kind of services. The other service that they don't give you on this list is Kubernetes. Now, if you go to AWS, you can get the Elastic Kubernetes service, EKS, from Amazon. But if you go and look at the Packet website and search for Kubernetes, you'll find this great blog post by Zach, the CEO. Oops, we forgot to build a managed Kubernetes service. And he means this a bit tongue-in-cheek. They didn't forget. This is not part of what they offer because they are kind of very purist. We're offering you a bare metal platform. So how are we going to implement Kubernetes on top of this bare metal platform? And that's where we at Kinfolk came in. So what were we starting with? So what we had to work with here was essentially the bare metal network compute with API control. So you can say, give me a new machine, and it'll spin up a new machine, pixie boot it, or however they do it behind the scenes, and then give you serial console access via SSH. There are a few services that you can get. So they'll set up a VPN access, but not kind of site to site, not across data centers. There's some storage capabilities, but they're not necessarily that easy to leverage. And there's a third-party object storage solution on top of it, which I don't think was a key part of what we were using here. But on top of this, we had to build essentially the same kind of Kubernetes environment that they were running in AWS. And I'll talk through some of the aspects of how we did that. And really, this is really focused on kind of what were the key problems that we had to address because we were running in bare metal. There's a whole lot more to putting together a full Kubernetes solution than just these things, but this is really kind of those things that are really impacted by the difference across those clouds. So first of all, we had to actually have a base Kubernetes environment to start from. And we started from a project that we launched recently called Locomotive. And this actually is based on a distro called, or an upstream project called Typhoon, which is itself derived from CoreOS's Tectonic. So if you've ever used CoreOS Tectonic, it looks and feels very similar, which means it's a self-hosted Kubernetes control plane. So the Kubernetes control plane is itself running in Kubernetes. It's got secure and stable kind of config out of the box, so things like network policies and pod security policies and providing updates and things like that we take care of. And we have a number of things that we call components. It's a layer that sits above the base Kubernetes distro that add all the essential ingredients that you need to put together a Kubernetes environment to deploy into. One of the unique things about Locomotive is it comes bundled with Linux distro that we build called Flatcar Linux, which is itself based on CoreOS container Linux. And so it's a super optimized, immutable OS, very lightweight, that sits underneath Kubernetes and is really kind of optimized for this environment. And a lot of what we had to do actually was not just on the Kubernetes side, but also making sure that Flatcar was optimized to run in the Packet environment as well. So the first thing I'm going to talk about that was in that list was load balancing. How many of you have run Kubernetes in a bare metal environment? Anyone show of hands? Okay, a few folks. So when you want to expose a service that's running inside your Kubernetes cluster to the outside world, right? If you look in the Kubernetes docs, it says there's this thing. You create a service as you would normally, and you just give it a type load balancer. And anyone know what happens if you do this in a bare metal environment? Nothing, correct. Prize for the guy in the back of the room. And if you look in the docs, there's a little the fine print here is that this all works for providing externally accessible IP addresses into your cluster, provided your cluster runs in a supported environment and is configured with the correct cloud load balancer provider package. Right? So this will integrate with Amazon's ELB service or some cloud load balancing service, but in Packet, there is nothing like that. So we had to work out, the first problem we had to solve was how we're going to do load balancing. And we started with a project that we've integrated called MetalLB. This originally came out of Google. One of the developers in Google built this, and it allows you to expose your ingress controller. So in our case, we're using Contour in the cluster for ingress control, and allows you to expose that via external IPs. And MetalLB itself runs in the Kubernetes cluster, uses standard network protocols, and allows you, in particular, what's one of the nice things in a Packet environment is they give you BGP access to the top of rack switches that you're running on. So you have real access to the underlying networking hardware, and just try and get that out of Amazon. Amazon is not going to give you that level of peering control into their physical hardware. You can do that here at Packet. So it'll advertise these IP addresses of your services to the physical network via the IP routing protocols, and then you can use equal cost multipath routing (ECMP) running across all of those switches. If you're advertising the same address from multiple machines, the hardware will automatically load balance across them. So this gives you high availability using the BGP convergence, but it also gives you really high performance external load balancing. So if you've not looked at this project, you have some bare metal kind of applications, I recommend you do. There are some gotchas. There are some things you need to understand with it. We've come across. So the first is, and this is really just kind of a caveat with ECMP in general, but you need to understand how ECMP works. It does fairly simple load balancing. So if you have multiple racks, you need to make sure that workloads are balanced across those racks in order to get good load balancing. The other thing which we've been looking at is we use Calico for networking. And if you want to do Calico BGP peering to the top of rack switch, and MetalLB is also peering to the top of rack switch, now you've got kind of conflicting BGP peers that you're trying to set up. There are ways around this, and I'm actually talking with some of the folks at Packet who've done this, and we want to do this, but this is on our to-do list, is to optimize the networking to be able to make the most of Calico's non-overlay networking for the best performance. So those were a couple of things we came across with MetalLB. On the next thing that we wanted to address was really around security. And I mentioned we use Calico for networking. A lot of people do. A lot of people are aware of it for its ability to do network policy for Kubernetes pods. So you can specify within a Kubernetes cluster which pod can access which other pod. And that's all pretty well known. One of its kind of secret features that not a lot of people know about is its ability to do host protection as well. So this allows you to actually protect the F0 interface on your host to say who can get access to that node. So this is nothing to do with Kubernetes. This is just about protecting that physical box. So this compensates for the fact that you can't easily set up global firewall rules across your nodes in a bare metal environment without a physical firewall in place. And you don't need to put a virtual firewall there. And it's just automatically enforced across all the hosts. So now you know that you can say exactly who can SSH into those nodes, and you're going to be protected that only those sources can do that. So it uses a very familiar Calico policy model. You can apply labels onto hosts in the same way that you would apply them onto pods, and it just does very easy updates. I think the slides will be available as a link here to instructions for how to do this. And the policy model just, as I say, is pretty simple. You're selecting, in this case, we're selecting for all those nodes that are labeled worker, and we're saying allow TCP on port 22, so for SSH access from this specific management address range. And you can also use things like global network sets to manage those IP address ranges via labels and things like that. So this is, if ever you're looking at how do I protect a host, particularly within a Kubernetes cluster where you might be using Calico anyway, this is super useful, kind of hidden secret capability of Calico. There are a couple of kind of future things that we'd like to improve with the host protection capabilities in Calico. The first is there's a little bit of manual work you have to do to actually create the record for the node in the Calico data model. It'd be great if that could just be made automatic from the Kubernetes control plane when you create a new Kubernetes node, that it creates a new host endpoint. We've automated our way around that, implemented that, but it's certainly a suggestion that we've made to my former colleagues at Tigera working on Calico. The other thing that we're seeing is we've actually been, our team's been doing some work along with Tigera to implement XDP support in addition to the IP tables support, which is how Calico currently implements these firewall rules. And we'd like to try that out because it gives you, certainly in theory and based on the performance profiling we've done, significant advantage in terms of denial of service prevention because you get a lot earlier in the stack. With XDP, you can take those rules and rather than implementing them in the kernel data path, you can get all the way down onto the network card with a smart NIC, or just earlier in the stack in the kernel using BPF. So some things that we'd like to try that we have on our to-do list. The next item we talked about was storage, and the solution we came up with here is OpenEBS. Who's heard of OpenEBS? Okay, a few people familiar with it, but not kind of yet got universal recognition maybe among the Kubernetes community. I think that may be changing because I think this is a really good project. It's certainly got a lot of promise from what we've seen. It is a Kubernetes native project for really container attached storage. So a lot of really nice attributes of it. Basically takes underlying storage, block storage, and presents it as dynamic pools to the application using ZFS. You can turn on replication, so you can have effectively the same, the same storage appearing across the cluster, and it implements high availability. So if you get a pod dies and another one recreates somewhere else, you can have the storage just pick up for the new pod from where it was. And it's really nice. We're using Prometheus for monitoring everything. So, like a lot of Kubernetes native projects, it's putting its metrics into Prometheus. So we quite like this. It is pretty early still, so there are certainly some rough edges that we saw. So there are areas where there were some manual operations required and for some ongoing operations. But we certainly, in fact, we found it bought us quite a bit in terms of management of storage compared to just using the local storage and trying to manually provision and manage that. One kind of caveat that we hit was making sure that if you've got an application layer or a layer sitting above storage, which is itself managing replication of data for high availability and in the way that Kafka does, then you don't want to be turning on replication at the layer underneath as well. Otherwise, you've got kind of contention there. The last area that I talked about was autoscaling, and one of the things that's important in this particular environment, but I think in a lot of environments, one of the things people like Kubernetes for is the dynamic scaling of workloads based on demand. So there's a Kubernetes API called Autoscaler, which allows you to not just scale up pods, but actually scale up the nodes in the cluster. So creating, if you're running an AWS, it'll create a new VM, stand up a Kubernetes worker image on it, and add it into the cluster. So there are multiple cloud providers supported here. Packet is not yet one of them. So This is something we don't yet support in the environment that we've got, so it's one of the things that we're looking to add, and we're working with the Packet folks to get this added. There is an active project on this. We're hoping that'll be coming very soon, and then we can actually drive some even greater efficiencies out of this deployment, because at the moment we're having to slightly over-provision and manually provision nodes. So when this is automatically happening, I think it's going to be like, super seamless. And one of the nice things about it being tied into the bare metal provisioning is, this auto-scaling, it really is standing up a new physical host and adding it into the cluster, which I think is really cool. So just to kind of come to the bottom line here of, just to give you some real idea about what a project like this looks like. We'd had a small team on this, and from kind of the point when we kicked it off to having their production traffic going live was just 3 months, which is a pretty accelerated time frame. And that was driven by some pretty strong business imperatives that they had to get off in that, or to move into Packet in that time frame. But once we've moved, in terms of what they were saving on a monthly basis, just on their cloud hosting bills, the amount they were reduced, the whole project paid for itself within the first 3 months of it going live. So from my perspective, that kind of is a financial no-brainer. And as you can see from the quote here from the director of engineering at PubNative, he's saying that as well. And on an ongoing basis, this is going to be saving them at the current rates, many hundreds of thousands of dollars. But going forward at the kind of growth that they're hitting, you could see that being millions of dollars pretty soon. And I think that the key thing that I heard from the customer was, even though the driver initially was just taking advantage of these cost savings, once they have this set up, now they have a whole lot of flexibility in place. Because now they have an environment like that picture that I showed at the beginning, where you've got 2 different clouds. Every time you're introducing a new service, you can say, where is the cost-optimized place to deploy this? Or latency optimized, or geolocation optimized, or whatever it is, and you've got the choice of deploying across any of those environments and of load balancing across them as well. So, actually, even though the cost was the original driver, when they're looking back on the project and saying, what have we got out of this? This is, I think, what they're most excited about, is that flexibility that it buys them for the future. So, so that's the story I had to tell today. I think I've got maybe 5 minutes left, a couple of minutes left. If there are any questions, and I'd be happy to take any. Okay. It's too hot for anyone to have a question. Okay, well, thank you so much for your attention. Oh, sorry, we do have a question there. Yeah. Yeah. So for the folks on the recording who couldn't hear the question, the question is, how on earth do you auto-scale when what you're provisioning is physical nodes, basically, right? And that basically comes down to, how does Packet work as a cloud environment? Because they do literally give you exactly that API access to say, give me a new physical machine. And there's all sorts of magic in their control plane behind the scenes, and there are a couple of folks from Packet here who I'm sure will be able to tell you about that. But that's essentially what they are providing, is that API control to physical machine provisioning using kind of the network boot processes that machines have these days. And I think yes, obviously that's available in their cloud. Potentially, if you have your own data center, you can talk to them. Can you take that software and deploy that in your own data center as well? Okay. Yeah, good question. So right now they're separate clusters on each cloud. So we've only built the the Packet environment. So they have a separate Kubernetes environment that they have in AWS. It's certainly something that we're looking to do in the future is to build, to replicate more of what we've done in Packet in an AWS environment and provide more kind of federation or capabilities across the make them more similar. But now, right now, they are quite distinct. But that's kind of the beauty of Kubernetes. It's a common API. Yeah, great question. So the question is, do we optimize for ARM? Right now, these are running on AMD machines. So there was some optimization we had to do for these specific machines. So there's some performance work we had to do in the Linux kernel to get the most out of that environment. ARM is something that's on our list of things we'd like to go do next. It is a platform that is available in Packet and in AWS as well, obviously. Okay. Great. Well, thanks so much. I'll be around here for a few minutes afterwards if anyone has any further questions, as is Chris, who's our CEO at Kinfolk and was very closely involved in the project because, as I mentioned, I've only been there for one month. So if you look at the timescales, you'll realize that means I wasn't around for most of this project. But happy to talk more with you and appreciate you all coming and joining us today. Thanks.